All right. So I'm going to talk about arrays, and of course, all of you know what arrays are. Most languages have arrays. They're fixed size collection of elements, typically of the same type, and they are an important implementation concept in that, unlike lists, arrays occupy contiguous places in memory. So if you declare an array of size 10 or 10 integers or something, it's a contiguous piece of memory that holds that array of integers. A list is not necessarily like that. A list, you have one element of the list in one spot of the memory, and then you have a pointer to another element of the list that may be somewhere else on the heap, right? So that's the difference between arrays and lists. And so arrays tend to be a lot more efficient, because when you want to access some element of the array, element at position number 2, then it's very easy to make the calculation and access directly, know exactly where this piece of where this value is, just if you know the size of each of the elements of the array, right? So you know the beginning of the array, you know the size of each of the elements of the array, so you can access directly the element that positioned at index number 2. And that's not true of lists, right? So at least if you want to access the third element of the list, you have to follow pointer, so it's a lot slower. So, and of course, you probably all know about different sizes of arrays. So you have one-dimensional arrays, also called vectors. You have two-dimensional arrays that are typically called matrices or 2D matrices, and 3D arrays, 4D arrays. So, and multi-dimensional arrays are the stuff of calculus from mathematics. And so how do you implement, for example, a two-dimensional array? Again, using the same idea that arrays are supposed to be continuous blocks of memory. So if you have a 2x2 array, for example, or something like this, which visually makes sense for us because that's what we're used to in mathematics, kind of having a matrix like this. In memory, it does not look like this. In memory, it's just a continuous piece of memory, but it's very easy to go directly to some element on this matrix just by doing the right calculations. You know the size, right? You know the x length, the y length of the matrix. So any ij element of the matrix is very easy to calculate exactly the position in memory where to go. So you don't need to traverse anything, right? So that's the idea behind arrays. Now, you all know arrays, okay? And I'm not going to explain to you what arrays are because you already know, but you may not be aware so much of array programming style. Array programming style is something that is, of course, based on arrays, but it's not sufficient. In order to do array programming style, it's not sufficient. It's necessary to have arrays, but it's not sufficient, okay? And in fact, lots of people have arrays, for example, in C. Arrays are widely used, but the style of handling those arrays in C is not array programming style at all. All right. So what is array programming style? So array programming style is something that perhaps some of you, especially people who come from an engineering background, may be more familiar with, that you may have encountered in systems like MATLAB, for example. Okay, so it's basically operations that apply to an entire array at once. Okay, so they are concise primitives about data manipulation. They are highly parallelizable. They can be done by specialized processes, like, for example, graphics processing units and others. So array programming is based on the existence of arrays, but it's more than that. Is the existence of a set of operations and then a sort of an API style that applies to the entire array as a whole. That basically, as you will see, you avoid iteration. That's the important key. So let me go down on this idea. So here's an example of the old style, C style of dealing with arrays, right? So this is, you have an array over here of strings, and then you iterate through the array, and you do something with each of the elements of the array, for example, lowercase or something like that. Okay, so that's something that you see, you know, all the time in imperative programming, right? In all of imperative programming languages and stuff like that. And here's another one. For example, we have a another thing that you may want to do with this array is to find elements that contain the character O, and then you construct a list that has only those elements that have the character O, right? So, but the what's happening over here is that you have an array, and then you are doing this iteration through the elements of the array, right, in order to do something, and that something is not very clear. You kind of have to read really like what is going on inside the for loop, basically. Right, so this is iteration in scalar languages, C, Java, you know, you name it, C#, all of the imperative languages. This is the style that, you know, we have arrays, but it's not array programming style. So what am I talking about? So what I'm talking about is operations that apply to the entire thing. So something like, for example, if you have, here's the array, and now you say some operation, I don't know, you know, 2 lowercase, okay? And now you will apply this operation to the entire array. Or it could be cars dot 2 lowercase, something like that. Or something in the other case, the slice of cars that contain the letter O would be something like, you know, where cars contains the letter O. So these would be operations, okay, that apply to the entire arrays. Not that basically you don't specify any iteration. And basically, the explicit iteration is replaced by powerful declarative expressions within the array. So it's called the reason for this, and the reason why this is interesting, okay, why is this interesting? You may want to ask, why is this better than the thing that I just showed you, that it's probably what you are used to? The reason is that by getting away from explicit iteration, we give the compilers a lot more opportunity for optimization. That's the reason. So if we do this, the compiler is stuck. You know, it's very difficult to optimize for loops. And the compilers try, you know, there's lots of smart optimization techniques that do program analysis, and they try to optimize the for loops. But there's only very limited optimization opportunities when we define and decide that we want to iterate through an array. Okay. When we don't say that, we want to iterate, we just want to do something at the high level with the array, then the compilers can do a lot more. They can parallelize these operations, okay? They can run it on GPUs, they can run it on several CPUs. So there's a lot more opportunities to parallelizing here. It's called vectorization opportunities, and that's the important thing. We say what we want to do, but we don't say how. That's the essence of declarative programming in general. So array programming style is a set of it's a set of constraints that tell you that what you do with the arrays is high-level operations that apply to the entire array, high-level declarative operations that apply to the entire array. We don't use iteration. Okay, that's the idea. So it's short. So something like this, as you can see, it's also much nicer. It's shorter, more concise, more declarative. The abstraction of implementation details allows for optimized implementations like in GPUs and other architectures. Same thing here, for example, here's an example of what are we doing here? We are adding A to B. Okay, so we have 2 matrices, and we are adding, we are updating the first one, A, with adding the values of the second one. And this is kind of hard to read, right? This is very hard to read. Whereas if you do this like this, it's pretty obvious what we are doing here. We're overriding A with, you know, the sum of A and B, right? Now, this is stuff that some of you who know MATLAB may be very familiar with, because MATLAB is actually an environment in the programming language that allows for array programming style. So MATLAB is a very well-known, you know, engineering tool, and of course, I will explain a little later. There's the reason why engineers have flocked to some of these ideas because it's a lot of calculus in engineering, right? In matrices and manipulating vectors of multidimensional vectors. And so it's much, much, much more convenient to express things like this than with explicit iteration. More convenient and it's better for optimization opportunities. So languages with array operations, actually, the first one is actually quite old. This dates back to the 1960s, early 1960s, with a language called APL. APL stands for A Programming Language. Very crazy name. It could also stand for Array Programming Language, but it actually stands for the title of the book that Iverson wrote, A Programming Language. So a basic also had some array operations in the 60s. And then this whole idea, this whole thread of programming ideas kind of made a left turn in a way that it's sort of the main programming language, general purpose programming languages like C, Pascal, and C kind of diverted it. It stayed away from arrays. And then there was a whole other set of languages, the engineering languages like S for statistics, which is a precursor of R for statistics, and then MATLAB, and then Fortran. So the ones that are used for engineering applications continue to use those ideas of array programming because they're super useful. And more recently, these ideas kind of made it again to the mainstream programming, general purpose programming languages in Python by Python's NumPy package, which is implemented in C. But basically, NumPy gives Python the ability to have arrays and a very powerful set of array primitives, array operations with which you can manipulate the entire array. One more recent is Julia. So Julia is a functional programming language that is also an array programming language. So very powerful array operations. And again, in general, all of these languages have been developed and are targeted towards engineering and scientific applications. So applications that have to deal with a lot of matrices and data, basically. So they're not necessarily for enterprise applications for which Java kind of has been designed. So scientific computing, linear algebra, graphics, for graphics, this is also great for images and videos. So it's basically large fixed size data, and more recently for machine learning. So we'll see next week when I start talking about, some of the primitives for machine learning in TensorFlow and things like that. That's basically also, matrices. that's what they deal with, large fixed size data. So I'm going to talk a little bit more about APL because it's a really interesting language. Okay, I have some questions. Hold on. The book you have posted on APL, are there any relevant sections that we can focus on? I would say the introduction, some of these ideas of the introduction are interesting, and then you can skim through some of the, some of the chapters. I'll talk a little bit about APL. APL is kind of an interesting language. If C itself does not support array operations, how NumPy can support it by writing in C? Very good question. So NumPy is an API on top of C. So when you are programming with NumPy, you are programming with the API that NumPy offers you, right? And NumPy, as I will show you, because I have the example of term frequency using NumPy, it provides you that kind of API that's very much array programming style, and underneath it does whatever implementation it wants to do, in iterations or parallelization or something. We don't know. That's under it's the implementation of NumPy, but NumPy is implemented in C. So there are, of course, there are arrays in C, and that's NumPy is implemented on top of arrays in C. That's what it is. But the way the abstraction level is pushed up, right? It's not us, the programmers, who do those iterations on the array. It's the compilers, basically, and the implementation of the API that maps those high-level operations to lower level C operations and iterations or something else. We don't know. It could be iterations, or it could be parallelization. It could be a lot of other things. Yeah. Yes. So let me talk about APL, because it's a really interesting programming language. So the book came out in 1962. So we're talking very early. That's right. So the point is NumPy uses vectorized instructions and may also make use of GPUs. Exactly. So that's the thing. The NumPy uses very high level instructions, and how NumPy implements it, I actually don't know. I think a lot of it is implemented in C, but for certain architectures, it can generate code directly for GPUs. So there's all sorts of interesting things that you can do once you go into these vectorized operations. All right, so Kenneth Iverson, by the way, was the person who designed APL. He was working for IBM. This comes in the heels of Fortran, another language for engineering and science, in the 1950s. Kenneth Iverson won a Turing Award in 1974 for APL. So APL is an interesting language for many reasons. So first of all, so this was early on in development of computers and programming. Okay, so in the very early 60s, this was at the same time as Lisp. This was well before C or Pascal or the higher level programming languages. So it was very early on. So people were still experimenting with a lot of the computer things. And so IBM actually designed the whole computer architecture for APL. So APL in IBM was not just the language, but it was also the computer, including a specialized keyboard. Because APL, one of the defining features of APL is that it used a lot of very weird symbols that were supposed to be, like mathematics. So it was supposed to have mathematical symbols, but it had to invent a lot of symbols that mathematicians don't necessarily use. So it invented a whole other language of its own that kind of looks like mathematics, but the symbols are really very strange. So they had to do a whole keyboard that had those symbols that were used in the language. So that was an interesting thing about APL. Do I have it? I don't have a. Yeah, I don't have the picture of the computer, but anyway, there was a computer that was designed on purpose for APL. The main features is the basic data type is a multidimensional array. Okay, that's the basic data type. And then a special graphics symbols for math notation. I have an interpreter here. You can find interpreters of APL these days out there. And I can show you some of what I mean by the crazy notation. So for example, so this one, 2 plus 2 is obvious what it does. This thing, 4, 2, 3 plus 8, 5, 7. Yes, Aditya is saying, I have read stories of people feeding works of Shakespeare to APL and it could compile them. I don't know about Shakespeare to APL, but the most notable weird thing about APL is that at some point in the 70s, the geeks, the people who knew APL, they had this whole practice of the one-liners, so APL one-liners, which were entire programs, complex functions that could be coded up in one line of APL. So APL is so concise that you can do sort of very complicated things just one line. It's really unbelievable. It's super hard to read. It looks like garbage, but it's super concise. And I'll show you some of these things here already. So this one, 4, 2, 3 plus 8, 5, 7 is actually sum of arrays. Okay, so 4, 2, 3 is an array, 8, 5, 7 is another array, and the operation plus is the sum of those two things. Okay, so that's what it does. So here's your first weird symbol, which I don't even know how to type. This symbol over here, I don't know how to type. I don't know how people type these symbols. But if I click here, it shows up on the right side. So this is what I'm going to do. So this weird symbol is the range operator. So it generates an array between 0 and 10 or 1 and 10, whatever it is, 1 and 10. So this is sort of a range. This other one plus, and then the slash, and then the range of 100,000. This sums the first 100,000 numbers. So if I do this, it's the sum over that range. Okay, this one is the multiplication of the range of 10. So it's like it's a factorial. Now here's where it starts to get hard, very, very hard to read. So what I have here is the definition of the average function. Okay, so it's a function. So I'm defining a function, average, that gets this definition over here. And what this is the sum of whatever it's given divided by the count. Okay, so that weird symbol, I was trying to kind of debug exactly and trying to identify this symbol. This weird symbol means count of something. So if I do, for example, this, I'm going to copy this because I don't know how to type these things. If I copy this and I say 5272, this is the count operation. So it counts how many elements are in this array. So basically, the average is the sum divided by the count. So if I define this function over here, and then I do average, and then I apply it. So average of 1, 2, 3, 4, then I get 2.5. Okay. I don't know what this is. This is stored 10,000 dice throws. That's probably a random or something. I don't know what this means. It's a weird symbol. So out of these, how many ones? You can try to, this one's even weirder. So frequency of all 6 possibilities. Right, so this, oh, I see. So you have a dice, the dice has 6 possibilities, right? So 1, 2, 3, 4, 5, 6. So this throws the dice 5,000 times, 10,000 times. So this is the function. And then this, you call the function and you count how many ones are there in the sequence. And then this is the frequency of all 6 possibilities. So you can, let me run this. Here's the throws function. And now I said how many ones and how many, and this one frequency. Okay. So, but as you can see, if you think about how to do this in C or Java or whatever, how the kinds of operations that you need to do to count the number, to throw a random number between 1 and 6, 10,000 times, and then count the number of times that the number 1 occurs, and then count the frequency for each of the numbers, how many times they occurred, especially the frequency. Right, so the frequency for each of the 1, 2, 3, 4, 5, 6, how many times they occurred in that throw. You can see that your natural tendency might be to go, here's my for loop. Okay, here's going iterating the thing. And in APL, there's no iteration. You just declare things, and you have these very high level operations represented by these really weird symbols that you kind of have to know what they mean. But it makes things super concise. And so, you can you can do very powerful things in very, very short programs. That's the interesting thing about APL. So I recommend that you take a look at the APL book, because it's kind of interesting from a historical perspective to see what was in his mind in the early 1960s about doing, how he came to this idea of doing array operations. It makes a lot of sense, actually. So you can try with APL. Try with also with this interpreter online if you want. So what is the array programming style? So the main data type is an array. So basically a fixed size collection of elements. The iteration is replaced by high-level operations on the array. So it's similar to functional programming, you know, for especially map. Okay, the map function is somewhere in between, you know, kind of a common thing between functional programming and array programming, because your map, you basically array programming style is even higher level than the map function. The map function, you can map a function to every element of the array, right? You can do that, but the operation, you know, the declaration of, you know, counts the number of times that these numbers occur in these sequences. That's even higher level, right? So that's even a higher level. And basically, but once you have these operations, these very high level operations, you have your basic data structure, and you have the basic the high level operations on those kinds of data structures. Then what are the programs? The programs basically are, you create these data structures, you fill them out with with values, and then you search, select, you transform, you cut, you slice. So basically, the computation, the program is about doing manipulations of that data, right? That's how you do programs in these kinds of array programming styles. So having explained this, let me show you how to do term frequency, our problem in array programming style. That was one of the styles that I have the most fun doing, I swear. It really twisted my mind. Hello. Come on. So suppose that you have only arrays that can be multidimensional. That's fine, but you have only arrays, and you have higher level the operations on arrays. Suppose that you are not allowed to do iterations. Okay, that's the main constraint. You cannot do iterations. How are we going to do term frequency? Okay, so here's how we go. So I'm using NumPy, and I have a lot of comments to remind myself and to explain to you what is going on, and to me, because I tend to forget. And these array operations can be very powerful, but sometimes they're very hard to remember exactly what it is that they are doing. So I have a lot of illustrations throughout the code to see, given this example, hello world, how does this unfold from here on? So if you have this example, hello world, as an input with sequence of characters, then the first thing that I'm going to do is I'm going to create an array with this sequence of characters, right? So I'm going to create an array, and now I have, here's all my characters. It's an array of characters, and you will notice that I'm actually adding empty spaces in the beginning and at the end. And the reason why I'm doing that's a little hacky. It's not hacky, but it's to make certain things easier down the road, to know, to not have to special case the beginning and the end of the data of the data. So I'm guaranteed that my data always starts with an empty with the empty space and ends with the empty space. So here's my array of characters, okay, in NumPy. Now, the next thing that we are supposed to do is to normalize it, meaning put everything to eliminate the things that are not alphanumeric. I'm sorry, that are not letters, and then lowercase all the letters. So here's what I do to eliminate the characters that are not letters. So here's NumPy. This is part of NumPy API. So NumPy has a for characters in particular, you can check if it's alpha, meaning that it's a letter. Okay, the twiggle means not. Okay, so I'm checking for all the characters that are not letters. This is the not. I'm overriding them with the empty space. And I'm overriding them in place. So I'm saying characters of, and this whole expression that I have here is what's called a slicing operation. Okay, the slicing expression. identifies all the indexes in this array where this is true. Okay, this is maybe really complicated for those of you who have never done array programming, but let me repeat this again, and you can put this on repeat when you listen to the lecture again. This expression over here returns an array of indexes. Okay, it returns the array of indexes where this is true. So basically all the indices of the characters that are not letters. Okay, so in particular, it's going to return index number, this one, the first one, the one that has the comma, there was a comma, no, the exclamation mark, okay, the exclamation mark, okay. This is going to be part of this array of indices that's going to be returned. And then once you have those indices, you can apply them directly. You can index the character array with that set of indices and do something for all of them, okay? And that's what's going on in here. I'm putting them all as white space. Okay, and here's another operation is lower. So this is also part of the API. So I get the character array. I lower all of them. Now I only have letters, and then I update. You know, I basically reset the characters array to a lower character version of itself. So now at the end of these two things, I have almost like that, except that now everything is lowercase, and the question mark has been replaced by an empty space. All right, so I've normalized it to lowercase and removed everything that was not the letter. Okay, so now once we have that, the next thing is that we have a sequence of characters. Now we need to identify words. Okay, this took me a long time to figure out how to do this. Okay, and I will show you. Maybe I remember seeing at some point when I was trying to do this, some version of APL that did this in like one line too. So here's the problem. We have a sequence, an array of characters, and now I want an array of words. Okay, so there's the kind of a scale shift going on. So how are we going to do that? So the way that I'm going to do this, and I had to do a lot of research to figure out how to do this, is basically by finding the indices of the spaces. Okay, so the spaces are going to be the only separators. Once I've normalized it, the only separators of words are going to be the spaces. So I'm going to find the indices of the spaces, okay? And then once I have the indices of the spaces, I'm one step closer to finding the words, because the words are going to be non-space characters, sequences of non-space characters between space characters. That's what defines the word, right? So let me go one step at a time. So I find the indices of the spaces. So there's the where clause of the NumPy API. Where NP where characters equals the space, then I have an array of indices of all the spaces of the array of characters. Okay, so I get this. Okay, this is going to be the array that I get out of here. Now, here's a little trick that I'm going to do here. I'm going, because I want to. So basically, I know from here that the first word is going to be between 0 and 6. The second word is going to be not 6 and 7, because 6 and 7 is going to be the empty space again, and I'm not interested. But there's another word between 7 and 13, right? So I know that these ranges are meaningful, and some of these ranges that are less than 2, it just means that they're just going to be sequences of spaces that I'm not interested, right? So here's what I'm going to do. I'm going to double each index and then take the pair. So I'm going to repeat this index, okay? So the repeat operation is going to repeat the elements, and it's going to result in something like this. And now I'm going to what's called a reshape. I'm going to reshape. I have a one-dimensional array, And I want now a two-dimensional array that's going to represent, that's eventually my words, right? The beginning and the end character of the word. So the way that I do this is I transform this in a 2D by using the reshape operation, which is something that you will also find in neural network APIs because they are based on, array programming. So I'm going to reshape, meaning skip the first and the last. So I'm not interested in this guy. Otherwise, it would, my pairing would be 0, 0, 6, 6, and that would not be good. So I want this pairing 0, 6, 6, 7, 7, 13, 13, 14, etc. So those is what I want. So I'm going to get rid of the first and the last. So that's what it means here. I go from 1 rather than 0, and I go until -1, which is slash is the last one. Okay. And what I do here, and this is the part that is always hard to remember, is that this 2 represents the 2 dimensions. So I want to reshape it in 2 dimensions. I don't remember what the -1 stands for anymore. Does anybody remember what -1 stands for in NumPy? I should have left a comment to myself and to everyone. I don't remember what this stands for anymore, but I remember that the 2 means that I want 2 dimensions, okay? So basically, if I do reshape like this, then the resulting array is this one. Okay, now I have a 2-dimensional array. And this is pretty good now for me to try to find the words, right? So now I know that this is going to have a word. This is not going to have a word, because this is basically, it's just there's only a difference of 1 between one character and the other, means that there's going to be an empty space. It basically the sequences of empty spaces. But this is another word, and this is another sequence of empty spaces. So I'm going to remove the indexing to the spaces themselves. Okay. So I'm going to so these are my ranges, and now I'm going to remove the ranges where the range, the distance between this element and this element is less or equal than 2. Okay, so I only want to keep the ones that are greater than 2, where the difference is greater than 2. Okay, so I have this expression returns the indices of the elements of this 2-dimensional matrix where the difference between these 2 is greater than 2. Okay, all right. Andrew actually explained what the -1 is. And for those of you who are not looking at the chat right now, the reshape, the -1 makes it so that NumPy will infer the number of rows. You specify 2 as the number of columns. Okay, all right, thank you. That's right. So now I have I've removed these little guys, the ones that the difference was less or equal than 2, and now the resulting array is just this one, which is great. I found my words, right? My words are defined in terms of ranges of ranges of indices of this character space, right? So now I have my words. Now, this is the weird part, because I would have loved to be able to continue to have something like, so now we have these what's going on in here between lines 28 and line 33 is that I have this weird representation that is kind of, it would be possible for us to continue with this representation, but it's not very nice, right? So I would actually like to have arrays of actual words, right? So I'm going to I want to have something like this that has the actual words, okay, not just the indices. So what I'm going to do is I'm going to create an array that in the following way. So I'm going to take those ranges over there. I'm going to apply a function to each of the ranges, okay, to each of these, that it's going to get the character, they're going to index onto the characters, and it's going to grab, the sequence of characters between those 2 ranges, okay? That's basically what is going on in here. And this is this is not exactly array programming style. This is functional style. Okay, but I'm using maps and lists and stuff like that. And I'm creating a new array over here. Okay, actually, I'm sorry. Let me backtrack. I'm not creating an array. I'm creating a list of arrays. Okay, so what I get at the end of this is a list of arrays. Okay. And then what I'm going to do, I'm going to recode this as characters as strings. So this is the part where I'm really changing the data type, okay? So I have here an array of characters, and I really want to continue with an array of strings rather than an array of characters. Again, we could have done this entire exercise in the domain of characters, but it was going to be really difficult to kind of do, for example, removing the stop words, for example. We would have to do everything in array. You have to map everything to arrays of characters, and that was going to be. It was possible, but it was going to be super difficult to understand what is going on. So I'm kind of re-registering the data as arrays of words, strings, rather than arrays of characters. So here's what I'm going to do. So I have the list of these arrays, and now I'm going to create an array that has strings instead of characters. Okay, and this is how I do here. Again, very a functional programming kind of thing. I'm the core of this is that I'm joining the characters, right? I'm joining all the characters. And I'm stripping the white space at the end. Okay, and then now I have a new array that has the data type is a string instead of being characters. All right. Okay, so now we have an array of strings. Next, let's remove the stop words, because it's much easier to remove stop words with strings than with characters. Again, it would have been possible with characters, but it was going to be really nasty. So let's create an array of stop words. Okay, we blow them up, we put them into an array of strings that are going to be stop words. And next, what we're going to do is to eliminate out of these S words that we had, which is this thing that looks like this, we're going to eliminate the words that are in the stop words. So again, there's the not, there's the is in, okay, very high level operation of NumPy. It checks if the second argument, I'm sorry, it checks if the elements of the first argument are in the second argument. Okay, so that's what, and the not, the negation means it's not. Okay, so the non-stop words are the S words that are not in the stop words array. Okay, again, no iterations here. This is all high-level array operations. So we have the non-stop words array, and then finally we can count. And again, NumPy gives us this high-level API for counting things. So there's the unique NS words on there's only one axis anyway, and you can tell whether we want to get the counts or not. So we get the counts. So we get the unique words and the counts. You know, this is the part where you guys had to have a dictionary. Typically in your implementation so far, you had to have a dictionary to count things, right? So there's no such thing here. It's just the unique operation gives us that already. It just returns the word and the counts. Okay, and then sorting. Unfortunately, I couldn't figure out how to sort it in array in using NumPy, so I had to kind of fall back again to functional programming. So zip to unique and counts, and then you sort using just the sorted function of Python. And voila, we'll print out the 25 most frequently occurring words. Okay. So honestly, this was one of the exercises that I had the most fun doing, because it really stretched my brain. It's just like you kind of have to think completely different when you're thinking in terms that you cannot do iterations, you cannot iterate, right? That's the constraint. You cannot iterate. But now you have these collections that are now placed in these fixed size arrays, and that's all you have. Now you have these fixed size arrays, and now you have to do whatever you need to do by, selecting, filtering, finding out different ways of, this little thing over here, this part of the program was the part that I have the most fun kind of figuring out. How am I going to identify the words out of here, right? And so you are going to have to think something similar in your exercise for this week. So what you're going to do this week is take my program. Okay, you can do it in NumPy if you want, or you can do it in another, whatever you want that exists in REPL. And so implement a program that takes an array. It's very simple. It takes an array of characters, just like what I showed you, normalizes them, removes punctuation, and removes the stop word. So all this stuff is stuff that I already, have. You have here. Where did it go? Here. So you take basically this entire program up to removing stop words. Okay, up to here you can reuse it exactly as is. So the difference is now that you're going to replace. Actually, no. You have to start. No, it's not. You cannot reuse it exactly as is. You have to start doing some things at the character level. So you're going to replace all the characters with their lit counterparts. So and lit is a code out there, and there's actually many. So that replaces A with a 4, for example, and B with an 8. So there are many ways that you can. There's many ways that you can replace. Choose whatever you like. I suggest like the first of these guys over here. Okay, first options, and look at capital A as lowercase a. So replace the A with 4, the B with 8, the C with this, the less sign, the D with these two things. That's going to be interesting. Replacing 1 with 2 may be a difficult thing in arrays. So I'll leave you to figure out how to do it, or whether you want to do it at all, or maybe choose another lit code. Because arrays are fixed size, so adding more things to an array, you have to create another array. You cannot just insert things in the middle. You have to create another array entirely. So I'll leave you to think about these problems. Okay, these are the fun problems that you kind of have to think. So choose some lit code and stick to it, and figure out how to do it, how to replace characters with their lit counterparts, and then print out the most frequently occurring 2-grams. So 2-grams are all 2 consecutive words in the sequence. So what are 2-grams? If you look, for example, at this sentence over here, the first 2-gram is note that, and the second one is that you. The third one, you should. Fourth is should stick. Okay, so it's basically every continuous 2 words. Okay, does everybody know what 2-grams are? Okay, so now you have the words, right? You remove the stop words. You have to identify the 2-grams, and then you have to count the most frequently occurring 2-grams, the 5 most frequently occurring 2-grams. Okay, so what is going on in here? The things that I threw here that's going to make you think is on the lit part, the lit replacements, that some lit replacements are trivial, like A with 4, B with 8. Others are not so trivial. Okay, D with 2 characters. The ones that have 2 characters, you have to think what to do here. All right, so think. And the other thing that I also throw here that's going to be interesting is the identification of 2-grams. And I actually don't know how, I haven't thought about it, but my intuition, that's going to be very similar to the tricks that I used here somehow, to identify words, to go from characters to words. I don't know. I'm looking forward to see how you solve this problem. Okay. Any questions?
Are we allowed to do the same thing that you did for the stop words, like convert it? Okay.
Yeah. Use whatever you want out of my program. The only two things that are going to be really your problems to solve are the lit replacements and then the 2-grams. Everything else you can reuse.
We would have to, if we remove stop words before doing the 2 grams, we would have to convert it back to a list of characters after.
Not necessarily. I don't think you want to operate on characters for 2 grams. Because 2 grams are operate on strings. Right? So the 2 grams operate on, once you have identified the words, then it's, this is 2 grams are these 2 words, and then these 2 words, and then those 2 words. So I don't think you want to convert back to characters. Unless I'm missing something, which is possible.
No, I think that makes sense.
Okay. All right, so I think you will want to do this in NumPy and Python. I cannot think of any other programming language that might be available in REPL that would offer array programming operations. The other one that comes to mind would be MATLAB that you might want to do, but I don't think that REPL has MATLAB. So I think you need to do this in Python and NumPy. Maybe it has Julia. Some of you may want to try Julia. I don't know if it has Julia. REPL has Julia. Julia would be another one. Let me see. New REPL. Oh, there you go. So for the ones who want to try something completely different, you want to learn a little bit of Julia, try Julia. REPL has it. Okay? Yes, Aditya. Oh, R might be another one. You might also be able to do this in R. R is another example of an array programming environment. So you could do this in R too, I think. So the only, like, the absolutely, yes, please, APL. I'll give extra credit for APL. REPL have APL? I don't think it does. Let me see, APL. Oh my God, it has APL. Okay. All right, so extra credit for if somebody does this in APL. Okay. All right, so having told you this, have fun. This is a really the one that stretches the most out of, at least for me, it was the one that stretched most of my brain outside of my comfort zone. So just remember, the only kind of strict constraint is that you cannot use iteration. All right, and so in certain other, like in cases like this, where you cannot use whatever, if the API doesn't let you, if the array API doesn't let you to do these kinds of things, you have to fall back to like functional programming. Okay, so do functional programming, but just don't do iteration. I don't want to see for loops in your programs. Okay.